Hello and welcome once again for another ES340 video. So today this is ES340 Day 21 Part A, and there will be a Part B for this video. So at this point we would like to, now we've seen sort of all of the analysis that goes into the course, and I think that it would be nice to now, which is why I chose to do this chapter, to see an application of all of this work that we've done, all of the entropy balance equations and energy balance equations and exergy balance equations and such, seeing it applied to some kind of real world system. So we're going to actually start off by looking at the ideal case. There's the Carnot case, which is we could almost view it as the absolute ideal. And then we'll go to vapor compression, which is what many refrigeration systems, how many refrigeration systems are designed. And we'll look at the ideal case there, and then also back out from that and find the non-ideal case, the real world case, as we go. Okay, so here is an example of a Carnot cycle. Now, when we're dealing with a refrigerator, we obviously have to input work, right? The work in that case, obviously it's work per unit time that we're inputting. So we're inputting some kind of power. And the power, of course, you've seen your refrigerator, it gets plugged into the wall and whatnot. So power is supplied to something in the refrigerator, and in this case, that power being supplied generally is to the compressor. Okay, and what we can see is that we can actually walk our way through this cycle. So this would be the ideal. Remember, I said we were going to start with the ideal case and work our way to the real case. So we'll start with this ideal, then there's vapor compression ideal, and then finally the real world, which looks a lot like the vapor compressor ideal, but we'll get there. With inefficiencies, basically. But in any case, so we're going to input some work to the compressor, which you can kind of see over here. And when we do this, we're going to obviously do the compression phase, but we come across an evaporator going from 4 to 1 here. And that's where we draw out heat from the cold region, right? Where the idea of the refrigerator, of course, is to keep it cooler than its surroundings, so we want to draw heat away from it. And the compressor, then we run whatever the working fluid is through the compressor. And in the Carnot case, this would be an adiabatic process. And then we run it through a condenser where we have some heat that's going out into the warm region. So yes, we end up having to put that heat somewhere, right? So we try to pump it back out into the environment. And if you ever put your hand behind a refrigerator, you'll feel that it's a bit warmer back there than the rest of your house, particularly because of this case. You're pumping heat away from the cold region inside of the refrigerator. And then it goes through a turbine. So this would be the Carnot cycle for refrigeration. Now we can ask questions about the working fluid. So if we look here, when it goes into the evaporator, it's a mixture, a liquid vapor mixture, a two-phase liquid vapor mixture. After it runs through the evaporator and comes out over here at point 1, after it's gone through, it's still a liquid vapor mixture, but now some of the liquid has been converted to vapor. And you can kind of see this on the diagram, right? Here it's a low quality liquid vapor mixture, and here's a higher quality liquid vapor mixture on the TS diagram. That's what I'm showing here, what's being shown here. And then it's going to go through some other phase changes as it goes throughout. And I'm going to leave it to you to figure out what it is at state 2 and at state 3, because that's going to be the clicker questions. So clicker question 1, at state 2, the refrigerant is it a mixed liquid vapor phase? Is it a saturated liquid phase? Is it a saturated vapor phase? Is it a superheated vapor phase? Okay, so at point 2. And you should remember this from the diagrams that we've dealt with, PV, TS, and other diagrams that we've looked at. The second clicker question, we want to know when we go from 3 to 4, so that's when we go from up here down to here, going 3 down to 4 here. That process is called what? Is it isobaric? Is it isentropic? Is it isothermal? Or none of the above? Okay, so when it goes from 3 to 4 here, which of those is it? And then the final thing is we're going to recall that the coefficient of refrigeration, which is beta, is equal to Q dot in, so the heat that goes in, over M dot. This is operating, I should note, operating at steady state. That beta is equal to Q dot in over M dot divided by W dot net, the network, right, that's done. So in this case, the network would be would be WC minus WC dot minus WT dot, right? Because the work that's the network that's coming in is the difference of those two. Okay, but in any case, divided by the network in divided by M dot. For this refrigerator cycle, which equation would be most convenient for finding the Q dot in over M dot for beta max? Now remember, beta is whatever it's actually operating at. Beta max is the theoretical maximum value there. So you can say certain things about you can say certain things about certain terms, I'm going to leave it that way, in various equations if we're operating at the maximum theoretical value, right? And so which would be the most convenient? Would that be the entropy rate balance equation, the energy rate balance equation, or the exergy rate balance equation? Okay, so now let's move on. And we'll say the beta max is equal to Tc over Th minus Tc. And you can actually work this out from the diagram if you, from this diagram up here. This is still for the Carnot cycle, right? For the diagram up here, you can see that you can work it out so that you find that this is in fact the beta max that you would get out of the Carnot cycle. But we know that real-world refrigerators operate below the Carnot coefficient of refrigeration, right? So we know that they generally operate beneath this. Now, if we were still operating in a Carnot cycle, which is the idea that maybe that's the initial idea of how we would go about it, right? Is just to do the same steps that are in the Carnot cycle. But, maybe there's some inefficiencies that are introduced along the way, which makes this not operate at optimal efficiency, right? At the maximum efficiency, or the maximum, in this case, coefficient of refrigeration. So if we were to do that, if we were to go operate along the Carnot cycle, basically what we would end up with is we would end up with a TC prime and a TH prime, where we're operating in the real refrigerator would be operating at a cold temperature for the evaporator that's slightly lower than the temperature of the cold region that we're trying to get to, and the condenser is operating at a temperature slightly higher than the temperature of the outer room or whatever where we're pumping the heat into from the refrigerator. And the efficiency in that case would then just be very simple, right? It would just be TC prime over TH prime minus TC prime, because we would just have to find whatever those operating temperatures are. So this would be great in theory. We could do this, operate the Carnot cycle, but and just accept some slight inefficiencies. But there's actually problems with doing that. In real systems, there's something called wet compression, which makes things highly inefficient. So if you're doing if the working fluid is not exactly in the mixture that you would like, for instance, when you go through the compression phase, that's going to be an issue, and wet compression can ruin any kind of efficiency in the system. And there's also inefficiencies during the expansion phase that are introduced if you try to operate the Carnot cycle. Not to mention the fact that making adiabatic processes work is really difficult. So when you analyze all of those things, you find that actually trying to make a real world system that behaves like the Carnot cycle, just slightly less efficient, is not the way to go, at least for refrigerators. So we'll remind you of a couple of things. One was, we already have discussed this. If we, this also is operating at steady state. Something I forgot to mention. But operating at steady state, if we ignore the effects of kinetic energy and potential energy of the fluid, which are generally quite small relative to the power that's being put in and the heat transfers that are happening, these are very tiny quantities, so we kind of can shrug them off with a low percentage of error. That we found actually for a refrigeration cycle, that the coefficient of performance of the refrigerator is related to the enthalpies here, H1 minus H4, based on this process, right? Up here, H1, find H1 here, H4. You've already done stuff like this before in problems. So you find H1, you find H4, and similarly, you find H2, and you can find the coefficient of performance here. Now, as I mentioned, there are a bunch of inefficiencies that are developed by trying to exactly copy the Carnot cycle, but the vapor compression system allows us to follow a slightly different path without the trade-offs that would go with a Carnot cycle for issues that happen within the system. So the idea is we're going to trade some of the efficiency that you would have gotten if you had ran an ideal Carnot cycle into a slightly better design system, and by doing so in the real world, we get better results than trying to copy the Carnot system, the Carnot cycle. Okay, so here's the idea. Notice that when we go from 1 to 2 here, we do this part is isentropic, right? This is the ideal case. We would do an isentropic jump from 1 to 2. And notice that here we start off in a saturated vapor, and we go to a superheated vapor, okay? And then in the next part of the cycle, we go from the superheated vapor down to a saturated liquid, and then from the saturated liquid to the mixture, to get the mixture that we want out of the system. Okay, so this is the way that this kind of and this is going to be a compression here, right? Going back up here, we ran from 1 to 2 through a compressor, right? So all of these things are going to kind of match up. We run through the condenser going from 2 to 3. We run from 3 to 4. In this case, we run through some kind of throttling process. And then from 4 back to 1, we have the heat transfer phase, okay? Okay, so notice, again, we can kind of map out all of the states, as I mentioned. Where 1 is, 2 is, 3 is, and 4 is. Okay, but this still is the ideal case, right? So before we said, well, we can't really make the Carnot cycle operate. So how would we make something that operates similar but doesn't have some of the engineering issues that the Carnot cycle does? And so we can come down here, and this is the ideal vapor compression system. Okay, now what ends up happening in the real world is we don't typically end up oops, there we go. We don't end up right at 2s, but we end up at 2. And we don't end up at 3. In the real world, typically, we end up slightly off of 3. So somewhere down here. So this is generally what happens. I'll put a red dot instead of a... Okay, so this is what ends up happening in the real world, is we don't typically get quite perfectly isentropic compression because, again, there are irreversibilities in any real world system, right? There's going to be some friction. No matter how well built the compressor is, there's going to be some friction there. And there's going to be some losses in the throttling process as well. Okay, so this is actually what ends up happening in the real world type systems. Now, in the next part, we've discussed this, but we haven't really discussed the working fluid. So we'll discuss the working fluid in the next video. See you again soon.